We've seen the charging RC circuit theory. I'll briefly run through the discharging circuit theory. We have to begin with a charged capacitor. Q is equal to CV from the battery at t equals 0. So we'll take the Q infinity from the charging case, and we'll call it Q0, because now that's the starting charge on either plate of the capacitor, and we remove the battery from the circuit, complete the circuit again. What should this look like? We have now just a wire attaching the resistor back to our now charged capacitor. Well, what will happen? The electrons on the lower plate do not want to be together. They're going to start flowing back to where they came from, to the upper plate. This implies a flow of current opposite the flow of electrons. We'll call that I of t. You can see now that the current has reversed its flow direction in the circuit. It had been flowing from the battery clockwise. Now with the battery removed, the current will flow from the top plate of the capacitor to the bottom plate. What's our loop rule? Here, if we start in the same location and we travel clockwise again, the direction is unimportant, just changes all of our minus signs. You have a plus R times the current, and then we have a drop from a higher to a lower voltage here. Q over C gets us back where we started. Let's separate this differential equation. The current is just dq dt can move the r over here to obtain dq over dt is q over rc, which we'll call tau. dq over q is equal to dt over rc, or tau. If we're going to integrate both sides, we need dummy variables here. So dq prime over q prime should be integral dt prime over tau. At time 0, now we're starting with this initial charge, Q0, and at any generic time t, we'll just have lowercase q. So our natural log q prime, magnitude evaluated at our limits, is t prime over tau evaluated at the limits 0 to t. Okay, as before, both of these quantities, their magnitudes of charge on plates, are positive, so we'll have the difference of the logs equals 1 over tau t minus 0. Right, this is just the log of the quotient. should be our Q zeros, equals T over tau. Implicit in this expression is the fact that now the charge at any point during the discharge process, little q, will always be smaller than that initial charge. So you are taking the log of a number less than 1, and that quantity would be negative. So we could rewrite this if we want. Natural log Q0 over Q, of course, inverting the argument brings out that minus sign. Then we'll undo the log. We have Q0 over Q is e to the minus t over tau. Or Q of t is Q0 e to the plus t over tau, and I have a serious problem. How do I know I have a serious problem? This is a teachable moment. Of course, I could have just gone back and edited out the sign issue, but it's useful for you to pick it out on your own. Can you see the issue? Right? Clearly the charge on the plates is not going to grow exponentially with time. Implicit in our definition of I, in the previous charging capacitor case, we said that I is dq dt, right? It was the rate at which charge was being accumulated, magnitude of charge was being accumulated on either plate. So to remain consistent with the charging derivation, we must keep the same definition of current flow. All right? Even though we understand that conventional current in this circuit is going to flow counterclockwise, our definition of I demands that it is the rate at which the magnitude of charge on the plates is increasing. You can see that will change this sign. Now we're traveling with that current, I of t. It doesn't change this sign because we're still traveling from the high voltage to the low voltage side to get back to 0. Now we can carry through this fix. Minus signs throughout. And we land ourselves here, which is where we wanted to be, and that is exponential decay on each plate. Now the current can be quickly written the time rate of change of the charge on each plate. That's just Q0 minus 1 over tau e to the minus t over tau. So you can see that that current gets fixed. Of course, tau is RC, Q0 That initial state was CV. We have current negative V over R e to the minus t over tau. The fact that we have now a minus sign out front captures the fix that I knew I needed to make up here, right? In order to have a consistent construction and derivation of the solution for the charge on each plate of the capacitor, I needed to keep this direction of I consistent. The fact that our solution tells us that I is negative makes the conventional current flowing counterclockwise, as we knew it must. Quickly, what do these plots look like? We have charge as a function of time, and we have current as a function of time. I like to place the zero of current up here. The charge begins at Q0, which was our CV, and it decays exponentially. The current also decays exponentially, but it is negative and it approaches zero over time. Our initial value you might call I0. It's going to be negative V on R. Okay, so we start here and we decay up to zero. Briefly then, let's do another example. For the discharging capacitor, we could answer a question, how long will it take to lose half of the initial charge Q0. Just as we did in the charging capacitor example, let's restate this. What are we trying to find? We're trying to find T, say 1/2, when the Q on each plate, the charge magnitude, is 1/2 of the initial value. And so we start with the general expression. Q of T is Q0 e to minus t on tau. And we say that Q of time 1/2 is 1/2 of the initial Q. Q0s cancel, we have 1/2 is e to minus t 1/2 on tau. The natural log of 1/2, we're undoing the exponential, is minus t 1/2 on tau. And our solution for t 1/2 is then negative tau natural log of 1/2. Natural log of 1/2 is negative, of course, so we could invert that and write this as the positive tau times the natural log of 2. And this is the quantity, not the video game, known as the half-life. Half-life of the charge on the capacitor, or a similar mathematical expression will govern the half-life for quantities of radioactive materials over time that decay into less heavy elements.